All right, so yeah, thanks for the introduction, Orly. So I'll be talking today about machine learning-based virtual diagnostics for electron beam prediction and control. And an outline of my talk, I'll start with a brief motivation for machine learning-based virtual diagnostics, introduce sort of the terminology, and motivate why we think this is an interesting area of research, and we've been working on this recently. And then I'll spend most of the talk discussing some examples of virtual diagnostic work that's been done mostly at SLAC, because that's where I work and I'm most familiar with. I'll start with some prior art, which is previous studies that were done at facet 1 and LCLS. And then I'll discuss some simulation work that's been done for the upgrade of facet, the facet 2 facility, and a proof of concept demonstration of a longitudinal phase-based virtual diagnostic at LCLS. And finally, I'll discuss the two-bunch operation of facet 2 and simulations for virtual diagnostic effects for longitudinal phase-based prediction, including resolution limiting effects from transverse deflecting cavities. And then finally, I will speak a little bit about how we can use these virtual diagnostics inside of optimization algorithms to not only predict the electron beam distributions, but also optimize them for given experiments. And then I'll discuss some challenges and next steps. So first of all, a brief sort of very broad background of why longitudinal diagnostics are important for the two large accelerator facilities here at SLAC, that's FACET and LCLS. So these two facilities deal with the different experiments. The FACET facility, as Orly alluded to, is an advanced accelerator test facility, which has focused a lot on plasma Wakefield acceleration and structure Wakefield acceleration experiments in the past. And for these kinds of experiments, it's very important to know the kind of electron beam distribution going into your plasma or going into your advanced accelerator structure, as is illustrated by this figure from Soufras et al. 2008. They did a simulation study in which they essentially mapped out what's called the bubble here, the accelerating cavity that's formed when a very high intensity beam is incident upon a plasma. And they showed that the electric field inside of this cavity, which is shown here by the black and red lines, is strongly influenced by the presence of a witness bunch, of course, the beam loading effect. And of course, that witness bunch, the longitudinal profile of that can either maintain the Wakefield, give it the same sort of shape if it's not properly loaded, or it can nicely flatten the Wakefield so you can achieve uniform acceleration of a secondary beam. And so all that to say that it's important for PWFA experiments in general to know the distribution of the drive beam and the witness beam going into the plasma. And this is something that is studied at the FACET facility, which is shown here on the right, that I'll describe in a little bit more detail in a few slides' time. For the other large accelerator facility here at SLAC, the LCLS, it's typically one of the very important diagnostics is the longitudinal phase-based measurement, which affects the free electron laser performance. These are two pictures which show two different longitudinal phase spaces going down the LINAC and measured at the exit of the LINAC. And as you can see, they're quite different. They're very large striations, in this case, caused by the microbunching instability. And this is something that is well known to degrade the performance of the FEL. So having this kind of diagnostic in hand has been a blessing for the LCLS FEL. And it's something that they can measure readily. And I'll speak about it in a lot more detail in the next coming slides. So the quantities measured, as I said, at FACET, typically, there wasn't a full two-dimensional longitudinal phase space measurement, but rather there were two separate measurements of the projection and longitudinal phase space. One is an energy spectrum measurement, which takes the dispersed electron bunch inside of a bunch compressor and sends it through a small wiggler to generate X-rays. Those X-rays then map the dispersed electron distribution, which gives you the energy projection. On the other hand, the bunch profile, the longitudinal projection of the 2D phase space could be measured, for example, here using CTR spectroscopy. A paper by Tim Maxwell a couple of years ago achieved less than femtosecond resolution at LCLS. And really what we want is these two measurements at the same time. So the full 2D longitudinal phase space that could be measured using a transverse deflecting cavity, And unfortunately, this measurement is intercepting, whereas these two are not. And so this is where virtual diagnostics come in. So virtual diagnostic, for those of you who aren't familiar with the terminology, is just a computational tool which predicts what the output of a particular diagnostic would look like when that diagnostic is unavailable for whatever reason. And this can be based on either fast physics-based simulations or machine learning models. And the idea is that you take some inputs that you can measure on your machine non-destructively on a single-shot basis. You feed them to this either fast physics-based simulation tool or machine learning model, and you can get out a prediction of either, say, the longitudinal phase space or the transverse emittance of the beam in real time without intercepting the beam, and so you can use it for experiments at the same time. And there are some benefits to both of these approaches and challenges. So with the physics-based simulation approach, typically if you want to describe all of the dynamics in this process, the execution of these simulations is not so fast. It can take a few minutes. It may require high-performance computing resources on site, and even if you have all of these available, it often takes a lot of effort to replicate the machine behavior. And even then, once you've replicated the machine behavior, you need to account for drifts. So the other side of this approach is to use a machine learning model, which you can train offline using slow, high-fidelity simulations. And once it's trained, this kind of a model, whether it's a neural network or some other machine learning tool, can execute very quickly, which can give you this single-shot prediction of electron beam properties, which is desired. You can also do hybrid training based on simulation and measured data, which may be able to capture some of these unknown unknowns that are difficult to bake into your simulation a priori. The joint benefits of both of these approaches are that once you have such a virtual diagnostic running, this gives additional information for user experiments to tune on, an additional signal to feed back on, and also it allows you to interpret your experimental data after the fact, having more information available to you. So with that sort of brief motivation, I'm going to move into talking about some examples of both of these kinds of virtual diagnostics, computational and machine learning based at FACET and LCLX. So firstly, as I said, I'll describe in a little bit more detail the FACET schematic, because for those of you who are not familiar, this diagram may seem a little confusing. The FACET facility is was a 2 kilometer long LINAC, which accelerated the bunch from a thermionic cathode here all the way to 20 GeV through these bunch compressor modules and the final W chicane to the interaction point here. And the main goal for this facility was to demonstrate large energy gain for electron and positron beams in a single stage plasma Wakefield accelerator. As I said, the beams are generated by thermionic gun extracted from these damping rings. And this 2 kilometer long accelerator, being quite an old accelerator, has various systematic phase drifts, thermal drifts, and time varying uncertainties associated with it. And the longitudinal diagnostics that were present here was a TCAP that was located inside of the final chicane, which only streaked in one direction, though it didn't allow for bunch profile and energy measurements, but only bunch profile. The scintillating YAG spectrometer here that I just described in a slide ago, it allowed you to measure the energy spectrum non-destructively, electro-optic sampling, and diffraction radiation based bunch length monitors at the exit of each bunch compressor, which collect the radiation emitted in the last dipole bend and allow you to correlate that with the peak current of the beam going through the bunch compressors. So the challenge for the diagnostic system and the control system in this facility was essentially to stabilize the longitudinal phase space and the compression against drift. And in order to sort of tackle this challenge and address this issue, Alex Schenker and Spencer Gessner developed this adaptive method for electron bunch profile prediction, which is an example of the first kind of virtual diagnostic that I described based on online simulation tool. So what they did is they observed that the measured energy spectrum, the SYAG measurement that I was discussing earlier, correlated with the longitudinal bunch profile in a one-to-one manner. And so knowing this, they were able to concurrently run LI track one-dimensional longitudinal phase space simulations of the entire LINAC and guess the machine parameters in order to simulate the performance of the LINAC online. So once they had guessed the machine parameters and simulated with LeTrack, they got a simulated energy spectrum. They could concurrently measure the energy spectrum on the SYAG on every shot. And then what they did is simply compare the two spectra with LI-TRAC and use an adaptive feedback, in this case extremum seeking, to change the machine parameters to minimize the difference. The goal here being that once you achieve a convergence in this cost function, which is just the difference between the two spectra, you would also be able to estimate the longitudinal bunch profile, which you could only measure destructively using a transverse deflecting cavity. And what Alex and Spencer showed is that they were able to do this, and they were able to also do this in the presence of significant drift. As you can see, the actual TCAP detector intensity here versus what was predicted was quite satisfactory, also over time. And this experiment showed that at least for one kind of running configuration at facet, this was successful. However, there were a few caveats here that they mentioned in the paper. One is that the convergence rate and the accuracy of this is sensitive to the initial parameter guess. So it's very important to get this correct, otherwise you get stuck in local minima. But if you do indeed get this correct, one of the hopes of Spencer and Schanker and Gessner in this paper was that they wanted to use this one day as a feedback in order to tune desired electron beam properties. And as I said, the challenge moving forward from facet 1 to, say, facet 2 is that usually there are collective effects at play, which, for example, for facet 2, include Wakefield's microbunching, longitudinal space charge, and CSR effects. And these you can't model with LI-TRAC with a simple code completely. And so for LINACs or accelerators where the collective effects dominate the dynamics, you really would like a 60 phase space characterization. That requires kind of rethinking the way that you model the way that you model the dynamics, whether it's using a surrogate model, for example, or using some kind of reduced model. You want to capture these very non-trivial correlations that may exist in your beam, for example, shown in this figure by Alex. So switching gears a little bit, moving to an example of machine learning-based virtual diagnostic that was adopted at the LCLS1. This kind of diagnostic was aimed at the photon side. So it was trying to predict X-ray FEL pulse properties based on diagnostics that exist inside of the LINAC. And the reason that these experimenters wanted to do this is that the way that the X-rays are generated in the FEL process here at SLAC and at many FELs around the world is through spontaneous emission through the SASE process, the amplification of spontaneous emission, and that has intrinsically varies from shot to shot because of the shot noise microbunching changing on a single shot basis. And as you can see, these pictures are showing examples of spectra recorded from this two-bunch mode of operation, which fluctuate both in intensity in each color and also in the location of the peak for both of the colors. And many experiments that use this kind of two-pulse pump probe configuration, they want full X-ray characterization on a single shot basis, but you can't do this with the available diagnostics because they don't run fast on a single shot basis. And so what Alvaro Sanchez Gonzalez and others, a group from Imperial College, decided to do was to use fast diagnostics and a machine learning model to predict the output of slow diagnostics. And this is sort of the kind of virtual diagnostic which allows you to fill in the gaps of the information that you don't get from, say, a transverse deflecting cavity or a spectrometer. And what they were able to do is they took two, in this case, properties which are very important for pump probe experiments, which are the X-ray delay and the spectral shape. And they were able to predict that using neural networks, just from using the output of fast diagnostics that are available on a single shot basis. And this is a promising result, not just for LCLS, but especially in the future for high rep rate FELs, where You know that you won't be able to measure every single shot, but you still would like to have this kind of information available so that you don't waste a lot of your data and you can use it in post-analysis of your experimental results. So this was sort of the state of the art a few years ago, and this kind of work has since continued at SLAC. And so I'll discuss some examples now of some of the work that I've been doing with other people in the machine learning group to continue along this direction. And first, before doing that, I'll spend just a minute or so discussing the differences between facet 1 and facet 2. So facet 2, which is the facility that I work on now, the main goal is not only to demonstrate large energy gain in a plasma Wakefield acceleration stage, but to also preserve the quality of the beam going into and out of the plasma. And what we mean by the quality of the beam is preservation predominantly of the energy spread of the bunch and the emittance. And so in order to do this, we would really like to have direct measurements or virtual measurements of the beam going into the plasma and out of the plasma. Unfortunately, as I already mentioned at facet, the transverse deflecting cavity located upstream of the plasma intercepts the beam. So you can either measure it or send it into the plasma. And so one of the things that we're going to look at in detail is trying to make this kind of a measurement a virtual diagnostic. And the challenge here for the diagnostics and control is to measure the longitudinal phase space, as I said, and also stabilize the compression with respect to shot-to-shot jitter of LINAC parameters. As I'll show in the next slides, the shot-to-shot jitter of the LINAC parameters does cause significant differences in the longitudinal phase space, aside from just the normal drift. And so for those of you who want to look at these parameters in detail, I left this table comparing facet 1 and facet 2 for future reference. So the first study that I was involved in, involving virtual diagnostics at facet 2, was indeed making a virtual TCAP diagnostic. And this follows the kind of format that I was describing earlier, where what we do is we take many simulations of the facet 2 LINAC, in this case 5 to the 5 simulations, and we scan a few critical LINAC and beam parameters, which we know are going to cause large variations in the longitudinal phase space. In this case, we scan the phase, the RF phase, and the RF amplitude of the L1 and L2 LINAC sections, and also the bunch charge coming out of the injector. And the inputs that we feed to the machine learning model are a few measurements that we know we can take non-destructively. So that's, again, the set points of the L1 and L2 phase, the L1 and L2 RF amplitudes, and the peak current at the exit of the now 3 bunch compressors, which we can measure non-destructively using these diffraction and edge radiation based detectors that I mentioned earlier. And also the emittance at each bunch compressor, which we're hoping to measure with a technique that's going to use the interference of edge radiation. This is a project that's being spearheaded by Brendan O'Shea, which I won't discuss in detail here now, but it's currently underway. And the inputs to these to the machine learning model that I'll discuss also include random errors to simulate the accuracy of measurements. So some results from this kind of a study is we showed that the machine learning predictions were pretty successful at getting the right current profiles, at least matching them up with simulations given these 10 scalar diagnostic inputs. And you need not so many shots for the ranges, the scan ranges that we are looking at here. So 1/4 degree, 0.1% variations, which we expect, as I said, from just shot-to-shot jitter. And I guess the important point from here is that some shots we know will be beyond the resolution of our TCAP. In this case, for this study, I was just calculating the peak current based on a histogram of the macroparticle distribution, not yet simulating the smearing of the TCAP. That'll come in a few slides time. But we know that some of these shots will be too short for the TCAP to resolve. And so a robust way of tagging these shots will be important for us to trust the output of the virtual diagnostic, since we may get a prediction that says the peak current is 50 or 60 kiloamps, but in reality it's 125. And we won't be able to distinguish that just with this virtual diagnostic based on scalar inputs. We have some ideas of how to tackle that, and I'll discuss that in a few slides' time. So moving on to two-dimensional predictions, we use the same kind of method here, but now instead of predicting the 1D prediction, we predict the full two-dimensional longitudinal phase space. And we see a similar agreement between the neural network output and simulation data. You can see a histogram of the scores here. Most of them, have quite a high score. If this is a score of 0.53, most of the shots are better predicted than this. And we can see that from just looking at the output of the virtual diagnostic predictions and where they seem to have a worse prediction than others, it's mostly in shots where you can see the longitudinal phase space is kind of over compressed. So the head of the beam in this case is on the left, and you see that the high energy part of the beam in this case comes later than the tail, and this is actually not the running configuration that we're going to run, and we're going to be running in something that looks a lot more like this. And so because of this, there are fewer shots that are like this in the data set, and the machine learning model seeing less of these shots actually also has a worse prediction for those. So there are ways to circumvent this by strategically sampling the parameter space so that you don't have this dearth of data in this parameter range. And this is something that we're going to have to be aware of and actively try to understand when we go to train the virtual diagnostic on the actual machine. Another thing that you can do once you have the model trained up is that you can simply remove one input at a time from the machine learning diagnostic prediction to see which one of the diagnostics is most critical to get the prediction right. And in our case, we can see that without the peak current measurement after BC20, which is the third bunch compressor, the predictions start to get a lot worse. And that makes sense because in our case, you can see that the bunch is almost fully compressed, and the compression is really very sensitive to the RF phase. So if you have a small amount of jitter and the beam stands up fully upright, then the peak current it'll have a large effect on the peak current, and that's what's really measured by this scalar number here. So doing these kinds of sensitivity studies kind of tells you which of the diagnostics is most important and which ones you really need to calibrate well for this prediction to work properly on your machine when you're doing it, when you're running this live. So moving on to actual experimental studies of this kind of work, we did essentially a repeat of the experiment that I just described for facet 2. Instead of doing it in simulation, we just took some beam time right before the shutdown of LCLS a couple years ago. And we essentially, as I said, just repeated this kind of a study where we scanned two machine parameters here, and we generated a lot of different longitudinal phase spaces. These are not the kinds of phase spaces you would expect just from the shot-to-shot jitter of the LINAC. We deliberately scanned these parameters over a wide range to see if we could predict very different longitudinal phase space profiles. And the inputs to the machine learning model in this case are only 5 numbers. It's the phase and amplitude readbacks of the L1S accelerating section, the X-band linearizer, and the BC1 and BC2 non-destructive current readings. And the conclusion from this part of the study is that indeed in simulation and in experiment, we can get pretty good agreement between the machine learning model and what we can measure with the TCAP. So what else did we learn that was beyond the simulation study? Well, we did see that for most of the shots, the prediction was very satisfactory, but for some shots, the prediction was very much off. And we tried to understand why these bad predictions were occurring. And ultimately, we chased this down to discrepancies between one of the diagnostic inputs, in this case, the peak current reading after the second bunch compressor, and the actual current measurement that you get on the XTCAP, so your ground truth. So in a perfect world, these two would match and they would have a perfectly linear correlation, i.e. if the current is some value after the second bunch compressor, since there's no more compression downstream, what you measure on the TCAP should reflect the value that you read out here. But there are some cases where that's just not the case. So for instance, the peak current monitor BC2 reads something like 2 kiloamps, when your measurement on the TCAV reads anywhere between 3.5 and 7. And so what that means is that the machine learning model sees a 2 kiloamp input. It's going to predict a current profile that's something like 2 kiloamps, whereas in reality, you might have something like 4.5, 6.5. It's a large difference between what you predict and what you observe. And now, because when we're running this virtual diagnostic live online, we actually won't have the TCAV measurement available because we want to send the beam to experiments. We need to be able to somehow flag when these shots are occurring. And doing this is a subject of an ongoing study, and using a different input or a redundant virtual diagnostic is going to be important for trusting the virtual diagnostic prediction. Otherwise, you won't know when you're in this sort of region or when you're in the more linear region where you can trust the prediction. Moving on to the last example here from facet 2, I discussed the single bunch operation, but of course, in the plasma Wakefield mode of operation, we're going to be operating in this case with 2 bunches directly accelerated from the photocathode and then delivered to the plasma. In this case, this is the drive beam on the left, and this is the witness beam on the right. And in this study now, we're not just simulating the performance of the LINAC and dumping the macroparticle distribution to calculate this longitudinal phase space, but we're actually simulating the streak of the TCAV and the image that you get in X, Y, which then you can convert to energy time. And so with this kind of a study, we're able to actually hone in on what the resolution limits are of the TCAV and how this affects the machine learning prediction. And what we see is that, not surprisingly, you get good agreement between the machine learning prediction and the simulated TCAV measurement. And this also should start some kind of some animation where it shows that for different shots, you can see the machine learning model does a good job of reproducing the changes in the longitudinal phase space and also the current profile. And this is for similar scan ranges to what I showed before. So this is an encouraging and positive, this is something that we'd love to see in the control room, really, when we start this up. However, there's some caveats that because of the resolution limit of the TCAV, now you can predict this image very well, but does this image really correspond to the reality of what your beam actually looks like at the interaction point? And we know this is not true, and we can see this is not true because we can directly dump the particle distribution, compare it with what we measure on the TCAV, and look at the differences. And again, here we have a situation where there's some shots for which the machine learning model predicts the TCAV accurately, and the TCAV measurement accurately also predicts what you actually have at the interaction point. And that is shown in these 2 plots here, where you see the witness bunch peak current as measured by the TCAV on the x-axis versus the witness bunch peak current that's actually there from the macroparticle distribution dump, TIP. And you see that for most shots, this is accurately described, but for some shots where the beam is very short, this gets smeared out by the TCAV streak. And so you're going to be limited to resolving shots in the drive bunch case between 10 kiloamps and say 35. But once you hit this 35 kiloamp limit, you don't know if your real current is 35 kiloamps or if it's actually 100 kiloamps. So this is where you need to include an additional diagnostic, which is sensitive to these very short bunch effects that can go beyond the TCAV resolution so that you can flag when these shots are occurring or when you're in this good measurement region. And that has been the subject of ongoing work that's been done by Adi Hanukkah and myself and others. And these are plots that I got from Adi, which show essentially the difference between exactly what I was discussing, shots that are very high peak current and then are streaked and measured by the X-band TCAV, which measures a lower peak current because of the resolution limits. And you can see that there is spectral information that talks to these very short bunches. And of course, if the bunch gets shorter, the spectral information, the bunch will radiate more at higher frequencies. And so knowing this fact, we know that we're going to be more and more sensitive in the spectral domain to bunches that are shorter. And that's good because the TCAV is actually less sensitive in its measurement to bunches that become short. So the solution here is to train a spectral virtual diagnostic in tandem with the scalar virtual diagnostic to predict the current based on TCAP measurements. And again, this is work that's been done by Ari, and these two plots show that when you look at the spectral data, you can actually set a limit and a threshold based on the spectral information that will tell you which side of that good or bad measurement I was discussing earlier. So if you take the spectrum from these two shots and you integrate the spectral response within some frequency band, you'll know that high current shots will generate a larger response in this frequency band than low current shots. And so you can map the spectral intensity versus the peak current that you measure. Ideally, in a perfect world with no resolution limits, the spectral intensity and the peak current would be a perfectly straight line. But of course, because as I discussed, there are resolution limits to your TCAP measurement, at some point you flatten out and you plateau, and around the 35 kiloamp range. And you can see that there's a linear region here where you can maybe say trust the prediction of your virtual diagnostic if the spectral intensity is below this value. And if it's above this value, you should be a little bit more skeptical of what your machine learning model is predicting, because it may be getting the TCAP measurement correct, but it may not be reproducing what's actually there. And so we actually map this in a paper that's forthcoming, and you can see that in scientific reports soon. So finally, I wanted to discuss optimization of the longitudinal phase space using virtual diagnostics, and how you can use the prediction from virtual diagnostics to tune your beam to get the desired distribution for a particular experiment. So this is an example of optimization for the two-bunch configuration facet 2. And this was work that was done by myself orally and a summer student, Michael Alverson, a year ago. And the idea is now that we have the machine learning prediction of the longitudinal phase space, we can use this on a single shot basis and just wrap this around a conventional optimizer like Simplex to tune some of the machine parameters, in this case, the L1 and L2 phases and amplitudes, to get the desired phase space. So what we did is we dialed in a target phase space, which we just we grabbed from the data set, and we started. We knew what the solution was supposed to be for this because it was part of our simulation data set. And then we started a simulation which was very far away from this in parameter space. So you can see the initial settings are here, a few degrees off in both the L1 and L2 phase, when the machine learning model had really only been trained on this very narrow area of parameter space, which represents the shot-to-shot jitter that we expect. And then we wrap the optimizer around this, and we ask, can you find a solution that brings you back to this optimal setting? And even though the longitudinal phase space that the machine learning model predicts during this optimization looks kind of very strange, it doesn't resemble anything like what's in the data set, there's sufficient information in these images to be able to guide the optimizer to an optimum solution. And so the model here shows some ability to extrapolate from the training data and also interpolate. And this is an interesting case scenario, and it's something that hopefully we would never be starting so far away from where we trained in terms of giving it an initial guess. But this is a test that shows that you can actually be use a machine learning model that's been trained with training data that's not exactly in the range that you want to operate at, and then find your way back to the optimal solution by extrapolating and interpolating. Next, I wanted to discuss one example that's not from SLAC, in which optimization was done not to tune the longitudinal phase space, but to tune the electron beam profile and XY for the round to flat beam transformation set up at the Pegasus lab at UCLA. So this is a small accelerator facility which is located in the basement of the UCLA physics building, and they do a number of experiments here, one of which involves generating flat beams from the RF gun here and transporting them to a downstream screen using a triplet of quads. And what we did a series of experiments here where essentially we went down there, and the first thing we tried to do was to gather a lot of data from these flat beam generation by tweaking the quads and see if we could train a virtual diagnostic to predict this kind of flat beam distribution. And this was quite successful. We were able to train neural network models that predicted fits to the beams, and we, in the first experiment, we were able to also use this neural network model to tune the parameters of the machine. In this case, using a genetic algorithm to tune the flat beam quads to then once again generate a flatter beam, as flat as possible. And we were feeding in inputs such as the quadruple settings, steering magnets, the virtual cathode camera images, and the solenoid settings in this case. But one thing that was notable, or at least interesting for this experiment, was that we returned 5 months later after the beamline. There had been certain changes, magnets been moved back and forth, and they'd been doing a lot of different experiments. So you expect a lot of drift in the parameters. And we tried to see if the machine learning model of virtual diagnostic was still able to predict the flat beam, and it did still work with no retraining. It didn't perfectly predict the beam distribution, but it was pretty close. And this kind of speaks to the issue of how often do you need to retrain an ML model if there's distribution shifts. Of course, these virtual diagnostics are useful, but if you train the virtual diagnostic on, say, Monday, and then you need to spend 6 hours retraining on Tuesday, so you don't have any time for beam time, then it's obviously no good, and you're not going to get a lot of love from the facility directors, or people are not going to be happy to give you beam time. So it's encouraging that given a lot of changes and also given significant amount of drift, this kind of a virtual diagnostic was still able to predict a two-dimensional image. And now finally, one example of optimization using machine learning-based inverse models was taken from the same actual shift at LCLS that I discussed a few slides back. But in this case, you want to use the machine learning model in reverse. So it's not taking the prediction and wrapping it around an optimizer, but rather asking the machine learning model, given a target phase space, what should the machine settings be for me to achieve that target phase space. And this kind of experiment was done in tandem. So it was using the machine learning model to predict the machine settings as a warm start for then an actual conventional feedback, in this case, extremum seeking. And of course, you can see that Alex Schenker here and Orly and myself were involved, and Alex was interested in this because, as I mentioned earlier, with his previous extremum seeking work, there was the observation made that if you start too far away with your initial guess, then you won't converge, and your target phase space is not going to match what you get based on just your feedback operating alone. So we started with this kind of very wonky longitudinal phase space picture, try to get to here. With the feedback alone, you get to not very close. If you use the machine learning model as a warm start, then the feedback is then able to zoom in quite successfully, and you get something a lot closer to what you wanted. So this is another example in which the machine learning model can be used in tandem with just conventional feedbacks that we use all the time to optimize and improve beam quality for various experiments. So finally, putting all of this together, what are we going to do at Facet 2 with all of this prior experience and with all of the work that I've just discussed in the previous slides? Well, we want to essentially achieve this kind of digital twin operation where, while the Facet 2 accelerator is operating, we have a suite of virtual diagnostics at our disposal. So we have 3 transverse deflecting cavities at Facet. So that's 3 opportunities to train longitudinal phase space virtual diagnostics. One right at the exit of the injector, the photo injector. One is after the second bunch compressor, and one is after right before the experimental area. So conceivably, with 3 ML-based LPS virtual diagnostics, we could really have a mapping of how the transport works. And this should be very beneficial for understanding the beam dynamics and for setting up and tuning the accelerator on the fly. As I mentioned earlier, we also have actually 4 locations. There's also a dog leg here, which will outcouple edge radiation from, where these edge radiation-based diagnostics will be used to predict the beam emittance. And so now we have the beam emittance in the longitudinal phase space after each bunch compression stage. And we have at the final bunch compressor a location where we can install a target, a diffraction radiation target, to gather spectral information to do this vetoing of high current shots that are beyond the TCAP resolution when the beam is at full compression. And then we can also wrap all of these diagnostic inputs into two kinds of machine learning driven controls. So model independent ML assisted adaptive feedback, which is a long-winded way of describing the result in the previous that I discussed in the previous slide, and also model dependent reinforcement learning controls. And this is the idea and the goal for a series of experiments that have been approved at FACET, which will incorporate all of these virtual diagnostics into machine learning driven control systems to hopefully improve beam delivery to users for all of the experiments that are planned at FACET 2. So with that, I think I'll conclude and I'll take any questions. I've described some of the machine learning based virtual diagnostics, and I think these are promising tools that have been used at SLAC and at other places to aid in both machine setup, optimizing beam delivery for experiments. They can be used on the fly for data analysis to rapidly extract beam parameters, and also offline for data analysis and interpretation of experimental results. Recent work has shown the feasibility of these kinds of ML diagnostics in proof of principle experiments, and that sort of shows the potential of these methods, but it's really only scratching the surface of what we can do. There's still a lot of major challenges ahead. You want to be able to do this robustly and in an operational setting, not just be able to make this work once or a few times. And so for this, we need to accurately quantify how often to retrain which diagnostic, how best to combine machine and simulation data, and how to scale this up to complex modes of operation, two bunch, particular beam shaping techniques. These are, I think, the next major challenges to address, and we're actively working on them. So stay tuned for more results. And with that, I wanted to thank many of the collaborators that worked with me on all this work and whose work I presented here today, and also take any questions from any of you. Thank you.